Okay, so right now I have up the site for our WebMO. So the username is CHE-402, and you guys have the password there. So if you type in the password, click log in, you should be able to see something that looks like this. Yes? Okay. So if you click on new job and then create new job, gives you a blank screen. We talked about this briefly the last time we talked about this. What you're going to use a lot is the thing that looks like a very small periodic table. That's how you select the different elements that you're going to be dropping down. The next three down are for rotating, translating the image left, right, up, and down. The last one is zoom in, out. The next one down, the little arrow, is to like activate something for doing something else. Okay, so let us do one that isn't on the lab but is related. So it's the lab is C4H4. So let's just do butane, right? Or no, let's do a butene. One butene. So if you click on the periodic table looking thing, it brings up a periodic table. If we click on carbon, right, on the periodic table, now anytime we click, it's going to drop a carbon atom. So we're going to click to drop one carbon atom. If you click on an atom and then drag and let go, it will create a bond to that atom and drop a new atom, whatever you have highlighted. So I can click, drag, let go, and I have now made a carbon-carbon bond adding a second carbon. If I do that 2 more times, right, it doesn't have to be, so within the program, there's a button that will clean everything up for us. So you don't have to get it at perfectly, 109.5 degrees and do all that fancy stuff. It will take care of that for you. We can, once we do that optimization, if we want to look at a particular angle or something like that, we can manually adjust it afterwards. But generally for these, it's best to first build your molecule, hit the optimization button, and then futz with it afterwards. Okay, so right now we got C4. We can go about making butene, well, probably more than 2 ways, but there's 2 that come to my mind. One, well, I guess there's 3. One, we could add each hydrogen one at a time, right? So we'd have to add, what, 8? 2, 4, 6, 8, 10. We'd have to add, no, 8, double one. We'd have to add 8 hydrogens manually. Or we can go, one method would be, so let's say, first method would be click on hydrogen, and then let's say we want to add all the hydrogens that go onto this carbon, right? We want to rotate it around. The difficulty with this program is it's not smart, right? So that is not what a methyl group looks like. We can go here to clean up, down to either idealized or using mechanics. Idealized just sets everything to these specific parameters and makes all the carbon-carbon bonds a particular distance, all the bond angles, 109.5 for an sp3. The mechanics uses molecular dynamics to do it. Ends up being, the 2 structures are going to look very similar. For our purposes, it doesn't really matter which one you do. So let's do idealized. Right, so what it did was it took the 3 that I had before, put it in a tetrahedral arrangement, and then any carbon that didn't have 4 bonds, it slapped on enough hydrogens to fill up the 4, and then took everything and put it at, because in this case they were all sp3 hybridized, put them all in the arrangement to make butane, right? We wanted to make butene, which means we wanted a carbon-carbon double bond in there. So a method would be first make butane, pop off 2 hydrogens, make a double bond, and then reoptimize. Another option, and so we'll do it both ways. So we'll first do it this way, pop off 2 hydrogens, make a double bond, reoptimize, or when we were making the initial hydrogen, the initial carbon string, you can make the double bond then, and then hit optimize. Right? So whichever way mentally works for you the best. So the way that we delete the 2 hydrogens is we click on the arrow for adjusting or selecting. Click on one of the hydrogens and then just hit your backspace or delete button, and it gets rid of it. And we want to make one to this one, delete. And so now, if we want to rotate it around, we can rotate it around and you see that it's now missing 2 hydrogens. And so if we want to now make a double bond, we should be able to click on the adjust, click one, no, sorry. Go back to periodic table, click carbon, and then click on one carbon, drag to the other, and there, let go, and it made a carbon-carbon double bond. Okay, so to rotate it around to take a look. But if you look at it, it doesn't look right. Right? The hydrogens on carbon 1, right here, these look like they're sp3 hybridized. They should be more planar. So what we need to do is hit that optimize button again to now optimize the structure as we adjusted it. So we calculate cleanup, either idealize or with mechanics. Let's do mechanics this time. It does for the vast majority of the molecules we're going to do in this class, it will do either idealize or the mechanics almost instantaneously. We're not going to be making proteins. That is the bioinformatics class, not this one. So, okay, so we now have our 1-butene. If we wanted to calculate, so if we want to do a better optimization, the optimization it was using was essentially carbon atoms have a particular number of protons and electrons. If it's a carbon-carbon single bond, it has a particular force field around it, and it optimizes based on the average force field of a carbon-carbon double bond. So the idealized and mechanics are gross approximations. Right, so the carbon-carbon bonds are set to probably about 1.51 or 1.54 angstroms. We can check that by clicking on the adjust and then clicking to form a bond, and then it gives our bond length down here, 1.534. That's actually a fairly standardized carbon-carbon bond distance.
Where'd you get that from?
Click, so on the little arrow for adjust, and then you just click on 2 atoms, and it will give you the bond length. If we click on one more, it will give us the angle between the 3, with the second atom that you click being the apex of the angle, or the, I guess, fulcrum, however you want to call it, right? So the angle between, so I clicked on this carbon, then this one, then that one. The bond distance was 1.534. The angle is, slightly different from the 109.5 because it's better than the very vague, Vesper models. So it takes a little bit into account the repulsion from the carbons versus the repulsion from the hydrogens. So you get, even with the mechanics optimization, it's better than calling it straight SP2 or SP3 of 109.5 or 120. You get slightly better numbers, but we're going to see that if we do an actual real optimization using computational methods, that number will change. So this angle, 111.07 or 0.17. If we click one more, that dihedral angle. So if you remember from organic, right, the view, these little projection diagrams, right, the dihedral angle, let's say for butane, right? Well, I just put them on the exact same carbon, CH3, right? So the angle is the angle between these two. The dihedral, that would be the angle that we're measuring, is the rotational angle if you're looking down a bond. In terms of mathematics, it's the angle between the two planes that are made by three sets. So call this atom A, B, C, and D. So there's, in order to specify a plane, you need 3 points in three-dimensional space. As long as they're not all collinear, that gives you a plane. So there's a plane that is made by ABC, right? That specifies a three-dimensional surface. If you extend it out from there. There is another plane that is made from BCD. They're going to have a line of commonality down the BC bond. All right, so it's the two planes are going to intersect along the line of BC, and then the dihedral angle is the angle between the two planes. So mathematically, that's what we're talking about. Chemically, you can think about it as looking down the bond. What's the angle? You might be familiar with anti and gauche and eclipsed type arrangements. That's essentially what we're looking at, is the angle doing one of these Newman projections. Or Fisher. I think it's Newman. Okay, so doing one of these projections, it's the angle between the group that's on the back carbon, or the back atom of the bond, and the angle of the front atom on the bond. So we'd essentially be looking down this bond and trying to figure out the angle between this carbon and that carbon in that projection. Now, it doesn't have to be down a bond, right? An angle isn't inherent to chemistry, right? And the term angle is a mathematical representation. Distance is mathematical, and dihedral angle is the angle between two planes. So when we're specifying these, we don't necessarily have to have three contiguous atoms, three atoms that are one after the next after the next. We could look at the dihedral of this one, that one, that one, and that one. It'll give you a dihedral angle, so it's then essentially looking down. Select those fairly carefully. Looking down the line between this carbon and the back carbon. Right. So any four atoms you click, as long as they're not in a straight line, are going to have a dihedral. But chemical intuition-wise, and what's most useful for us, is to make it four atoms in a row, and then we're talking about the difference in the angle down the bond, right? But there will be some times in which we're trying to set up like transition states and things like that, where it's convenient to use some other atom as a way of moving something that's in the transition state, and so using the dihedral to move that atom ends up being convenient, even though it's not looking down the bond. Sort of giving you a preview of where we're going to be in a couple weeks. Right? So just to point out that the dihedral doesn't necessarily have to be down a series of bond. It's any 4 points gives you a dihedral. Chemically, it's most convenient to think of a dihedral as down a bond. bond and the two substituents on the other sides of that bond. Okay. So let's say we want to optimize this. The arrow down bottom right here says continue if you hover over it. Takes you to this page. There's a whole bunch of stuff that we can do in here. We're going to keep it simple for this first lab. Later on, we're going to start adding in all advanced and notes and all that sort of stuff. For now, we're going to keep it nice and simple. For the job name, to keep it so that we can easily find yours, why don't we start with your initials, then a dash, and then the chemical formula. Or well, chemical formula for all the ones you're going to be doing in lab is the same. So why don't we do your initials, dash, and then some form of a shortened version of the name. You don't necessarily have to type out the full name, but enough of the name that you can differentiate between the ones that you have. Or you could call it A, B, C, and D, right?
This is not a name. This isn't a name. It's just a
The name is going to be important so that when we run the calculations, it's going to go to a common queue. It's going to finish, and then you have to be able to find yours and know which one you're talking about. So that's the only part where the name matters, is so that you can find it later. So let's go here. I'm going to call this ACD-C4H8. Okay. We want to come up with a better geometry. So for this time, we're just going to do an optimization. So here for the calculation, this is the type of calculation you want to do. Drag this down to geometry optimization. Okay, on your sheet, it tells you the theory that we're going to be using. We are going to be using B3LYP. That's a very, very, very common computational method. It's fairly robust, fairly quick, and does a reasonable job. And then I think I have us using 6-C1GD, or is it DP? Okay. So that should be pull down. Oh, we'll just use 6-31GD. So scratch out the P. We're going to keep it simple this time. Okay, now the molecule that we were just doing doesn't have any charge, and the ones you're going to be doing today don't have any charge. So the charge is going to stay 0 for now. Later on, I think might do a lab where we're calculating the pKa's of things, trying to calculate the acid dissociation constant. So you'll have the neutral species and then the charged species that we'll deal with later. The spin multiplicity. Most of the things we're going to deal with are going to be singlet state. We might do some radical chemistry a little bit later, in which we'd have a doublet, but for now, keep it as a singlet. Okay, and then the advanced stuff we're not going to deal with today. So you just click continue, and it is churning. It shouldn't take too terribly long, but this is a website. Right? It doesn't instantly refresh. So you can force it to refresh, or you can wait. If I click refresh, refresh again. Okay, so Joy, yours finished. Mine is still going. Oh. So, one of the reasons that ours is taking longer is I think you started yours running sooner than I had. Right? And so you had a slight period of time in which you were using all the processors on the server. Because we're sharing the processors, we don't have all 12, and so it will take a little bit longer. And so now yours should finish up a little bit before mine. Okay, so what we can do is click on your molecule. We can actually see anybody else's. So when you look through, everybody should look fairly similar. They might be in different orientations, but because we all made up the same molecule, all the distance, and we use the same theory, method and basis. And we use the same theory to do the calculation, so everything about it should be the same. Okay, so if we now look at the carbon-carbon bond distance, remember last time it was 1.534. And that was for the, that one. So this one's a little bit different, 1.538. It didn't change by all that much, but if we were calculating like a really long carbon chain and each one shortened up by 0.007 or something like that, it might end up having some sort of matter in some way.
Yours is 1.538,
Yep.
mine is 1.533, it's okay.
Yeah, that's fine. It was the same. Okay. What did you end up with? 1.538? That's fine. Okay. Oh, yes. Not this lab. I wanted this lab to be a gentle introduction. Well, either next week or the week after, we're going to get into what all those numbers mean and what the input file actually looks like. Essentially, when it's doing calculating stuff, the computer has to come up with a variable name for everything. And so the first atom you put down is typically atom 1, the second one's 2, 3, 4, 5, and then so that numbers them, and that's how it does the calculation. It doesn't really call it carbon, it calls it atom 1, which has all these behaviors. Okay, so the values that you see are the numberings that are being used in the calculation. Okay. Now, if you look on the left-hand side, we no longer have all the same options that we did before. You don't have the periodic table. And the reason for that is we're now looking at the output file as opposed to creating a new input file. Right, so we're looking at the results as opposed to building a new molecule. So that's why we don't have the same options. But we could take this output, make it into an input by clicking on this arrow right here. Right? That essentially is saying, take whatever I have, make a new input file on it, and we can tweak it from there. Because all we did was an optimization, there's not a whole lot of information in here. There is a energy value. And this is something that's going to be important to you. So the number here, B3LIP, energy, the thing that has a unit of Hartrees, you're going to be writing down or copying and pasting that value into the table that's on the second page of your the lab handout that I gave you. You won't be writing down this particular number because that's not one of the molecules that you were supposed to make. But that number is going to go in the box under energy and Hartrees. Okay?
What would like the first one's frequency and
we are about to do that. You are jumping ahead. I like the enthusiasm. Okay? It has rotational constants and other stuff, so, but the frequencies that are on the sheet are the vibrational modes. Okay, so if we go back, we're gonna take this optimization and then click here. And now, did a quick flash of the screen, and you notice we got the periodic table back. Right, so this is now an input file ready to go, where it took all the geometries from the calculation we just did and pushed it into our input file. So if we now click on the two carbons to look at the distance, you'll notice that they're the same distance as you just saw. They're not that same 1.534 that they were before. They're now what it was they ended up optimizing them to. Okay, so we can now do a frequency calculation. So you click on continue. Do this, drop it down to vibrational frequencies. We're going to run it at the exact same theory and basis set. Now you can adjust the name, adding like a FREQ onto it, or run it as is within that job manager where we're looking at the files. It actually says what type of a calculation was run. So you'll be able to tell whether it was an optimization or a frequency. So we can just click here, right? You can see here it says from our previous ones, geometry optimization using Gaussian. It's really the only software we have. And the new ones say vibrational frequencies, right? So you'll be able to differentiate which one you're doing. Typically, determining the vibrational modes takes a similar length of time to doing an optimization. The key there is ballpark. So this time around, we got ours on about the same time you did, and so you didn't have free reign of all the processors, which is why yours took longer. Ours should be finishing up fairly soon. Okay. So while we're waiting for that, let's all just look at Joy's one. So by clicking it, we know that this isn't an input file because it doesn't have the periodic table. If we scroll down, we still have the energy. So we have the enthalpy, free energy. So we got the delta H, the delta G. From that, you can find delta S. Well, delta S is right there. Has the heat capacity. The entropy and the heat capacity and the enthalpy, I believe, are all calculated at 298 Kelvin, room temperature. Scrolling down a bit further, these are our vibrational modes. This one doesn't actually have activity in it. Okay. So, these are all the different vibrational modes that we got. We can look at one if we want by clicking on the little viewer, or the thing that looks like a film roll. And that would be, that's the frequency that corresponds to that particular vibrational mode. So down here at the bottom it says the vibrational mode number 2 with a frequency of 248.5 wave numbers or inverse centimeters. Scroll down, we can take a look at another one. So you'll be writing these out. The nice thing is, because it's C4H4, right, you won't have as many vibrational modes. Each atom you add on adds 3 vibrational modes.
How do you know which atoms are like vibrating? Cause like, you can only see it in the animation. This whole thing is kind of moving.
Which one are you looking at?
I think I tried the first one.
The first one?
Yeah. So which bond is like, which way? Pinpointed.
That bond right there is doing a torsional motion. The way that I can tell that is because I've done this for about 16 years. Right? So in a more advanced analytical class where you're really looking at vibrational modes, talking about wags, bends, stretches, asymmetric, symmetric stretches, that's where we talk about all these different types of motion. We will get into some of that, but way later. Yeah, so this is a torsional of the bond motion, yeah, or a rotational motion. So this would actually be considered the bond rotating around that bond. In your classes, typically they would have said, you know, when we're talking about vibrational modes in a class, we typically talk about them in more of a pure mode. So, you know, a CH stretch, we pretend when we're talking about a CH stretch that the rest of the molecule doesn't move. But you think of what's going on is you're moving away, you know, a center that has protons and electrons away, and so that changes the force field of the whole thing. And so typically the entire molecule is going to do some sort of bending and flexing. But one carbon-hydrogen bond, if we're talking about a CH stretch, is going to be moving a lot more than the rest. The rest of the molecule will bend and flex a little bit, but when we're talking about a particular CH bond bending and stretching, that's going to be doing the vast majority of the motion. Those stretches typically are a lower frequency. So probably somewhere around here. Lower. Try. There we go. Yeah, so that would be a CH stretch. You can see that a lot of other, I'm looking at number 27. A lot of other molecules are moving around, like this one here is bending and flexing a little bit. These two are moving a bit, but it's really that one that's moving the most.
So at that frequency, that's the vibration.
Yep. Yep, that is the thing that is doing the absorptions. We look at down here the IR spectra. That's what it ends up looking like. Now, I was talking with the guy who wrote WebML over the summer. They said they were going to be doing some new stuff where you can click on, our version does have that. Cool. Okay. So if you look at the IR spectra and then you click on one of these peaks, it should automatically load that vibrational mode. Those are the ones that show up on the spectrum. So if you click on the spectra down at the bottom, you'll notice that there aren't 30 different peaks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, so only 11 of them are IR active. That's all of them? Those are the ones that are active. Because what we're going to do is, on the previous one, it said that experimentally, when they look at C4H4, they chuck it into an FTIR. They find that those are the frequencies that they observe. So the question is, which structure agrees with those frequencies? You will have a heck of a lot less peaks.
Wait, so, the one that show up on the IR spectrum, right up here,
Mhm.
each piece, okay, so let's say 11 of these, and frequency, which is what, range,
Those are all the frequencies.
like literally all, okay, so, then we won't have it,
You will not have that many.
that's fine.
Those ones, no.
So what would you write for like the frequency?
Well,
I know we'll have less, but.
you'll have a lot less, and so you will be writing out all of those.
Numbers are easy to just write in there.
Yeah, so the one that's, oh, it does have, okay. So the frequency column, those are all the frequencies. Right, so that would be in your third column. You'll write all those out. For those, you can, round it off at one's place. Right, if you look at the frequencies that are listed here, there's a bunch of those. Yeah, so you don't have to write absolutely all of them out. The next column tells you the intensity of the IR. If it's in the 0, 1-ish range, you don't really see it. So the numbers that are in like the 30s, the 11, the 30, those are the ones that you're gonna end up seeing. Yeah, the other ones are probably either appear to be a shoulder, or you won't be able to see them at all. Okay, so you can either click on the IR graph at the bottom, or go through and just look for the biggest numbers.
So another thing, we write down.
Page 3 will show up. But if you click on the IR spectra, so first look at, sorry, go back, look where 3 falls, where that 3 1, 4, 7, 1,470. So you now look 1,472. Yeah, you can see it. It's that dinky, it's that one, right there, that's, yeah, if you scroll up to where you're almost touching, yeah, it's that really small peak underneath, yeah, no, just these big ones. So probably something in the 10 and above range is what you're gonna see. Okay? So, make up your molecules. There are, so one of the questions asks you to come up with one that's not there. So these are 5 options. There are, I think there's 3 others. 3 other structures that come to my mind, I might be missing one, that fill the C4H4 formula. Okay, so triple bonds, probably not quadruple bond. Anything that's a reasonable structure, so triple bonds are okay. It could be strained as all heck. Some of these actually already have a ridiculous amount of strain. Just come up with one more structure, and then in your table there's an empty spot. So come up with the structure, name it, and put it in there.
And if you had to have a original, just like all of sigma.
One of these. Something like that. Yeah, skeletal structure.
So really, yeah, it's the
Oh, to start a new one?
yeah.
Okay, so we're gonna do one more. We will do one of your list together. Okay, so you could go file. No, it is currently showing a vibrational mode. So we have to go here to the part where we're actually building the molecule, and then you can click file, and you should be able to click new. Yeah, and that will like this link. Okay, so let's do,
Wait, what do you?
oh, you first have to click here to get to the build mode, build molecule, and then you can click file name. Yeah. Okay. Now, on the original WebMO thing that I handed out last time, there is a link to the people that wrote WebMO that has a short guide. So if you get stuck, while you're in here, you can ask questions. But if you're, decide to do some of this at home, you can, and you get stuck, you can email me. By going to the site will probably get you a quicker response. Okay, so let's do the try-e. And I think that's one of them. So, tell me what I need to do.
Just drop 4 bonds.
How do I do that? Walk me through it.
Carry through, select carbon, and drop 4 straight bond. No, like straight bond. Then drag the bond 1, 2, twice, 2, 3, twice, 4 twice.
Okay. And then we just do cleanup, idealizer mechanic. You can also, over here on the far left, there's a thing that looks like a broom and a thing that looks like a wrench. Those are icons that do the idealize and the mechanics optimizations as well. So you don't necessarily have to go up to the cleanup and the drop down. You can do them from there as well.
Why does it keep changing the molecule the
Nope.
more you press on it? Like if you just keep pressing the brush, it'll just change the whole molecule. One more time. Last time last PhD we did just kind of like created dots and stuff. Yeah, I don't know why.
If you can reproduce the error with me standing there, I can maybe help you. But I haven't seen that before. Maybe if we do, so like this.
No, like it had like dots from the carbon 2 to like carbon 3 and yeah, it was
Okay, no idea. Okay, so we got this one. Now, previously, we had done first the optimization and then the vibration. We can actually do them coupled together. Right? So, I call this ACD dash A dash, oops, A dash, sure. I would be calling them ABCDE, and then have the formula. Whatever method works for you, use that. Okay, so now I'm gonna, instead of doing optimization, finish calculate, take the structure, vibration, we're gonna do them in one step. Alright. So we click on the optimize plus VibFreak. What that will do is we'll first do an optimization and then do a vibrational all in one step. It should take a decent length of time because we are essentially doing the exact same thing that we just did. Geometry optimization, that calculation finishes, and then it will take that structure and automatically load it into a frequency calculation. It helps if I push the button. There we go. Okay. Now, over here, these are some values for us. For the Chem 402, I've capped the calculations at 4 hours. If there's something that you want to run and you hit the 4-hour mark, you can always take the end structure that you had and look at it and then run it again. And so you're essentially taking the last structure it optimized to and then rerunning it. If we run into a situation where, you know, we're all running at the same time and it takes longer than 4 hours, which it shouldn't, just let me know and I can tweak. I can go ahead and tweak the setting. I have it set at 4 hours just in case you click on something. I don't really want the server tied up for days on end, which can happen depending on how we set up the calculations. Why is mine taking forever? Okay, so looking at this particular structure, right? We have the free energy, or sorry, this is this value here. Yeah, right here. Free energy, this is the value that you're going to want to write down. So that would be your delta G. It's not quite delta G formation because it doesn't do it relative to carbon as graphite and hydrogen as H2. It calculates it based on electrons next to protons. So if I think one of the questions is what's the difference in energy between the most stable structure and the least stable structure, right? I think I have that on there. You will take the two values, one subtracted from the other, and then there is the conversion factor between Hartree's and kilojoules per mole. So you'll subtract the two, take the difference, multiply by that conversion factor. What you'll notice is that for your molecules, the free energies are going to be virtually the same. They're going to differ in like the third or fourth, maybe the second or the third decimal place. And the reason for that, if you look at that conversion factor, it's 2,524 or 26, right? It's a fairly big conversion. Essentially, the first bunch of numbers are the energy of a carbon atom, the energy of a hydrogen atom. And so those have a lot of energy to them. When we're talking about enthalpies of formation and enthalpies of reaction, we're not talking about forming a carbon atom from protons and neutrons that are all by themselves. We're saying typically take this carbon atom, combine it with this one relative to carbon as graphite, relative to hydrogen as H2. And so that's why the values in the Hartree's, if you're just looking at what is coming out of a calculation, those values would end up being gigantic. Because it's the energy from taking free protons, free neutrons, and bringing them together. Whereas the calculation is asking you to do where you're taking the most stable and the least stable, that's an enthalpy of reaction. Right? Going between the two states as more something that we typically do in chemistry. Okay? We then have down here, you'll notice you have a lot less vibrational frequencies. Right? 18, that's a bit more of a reasonable number to write down. Wah, wah. Yes.
Right, so how do we do that subtraction for the difference? Like, just keep the negatives? Keep the negatives?
Yep. Keep the negatives in a whole bunch of decimal places. Just essentially type in the whole thing into Excel, the other whole thing into Excel, one minus the other, take that result times 2,524. 6, and then that's your answer.
So we just for people who just round it, like to 235.
Yep, round it to the ones place. And you can see that for your IR intensities, a whole bunch of them are in the zeros. It'll only be the ones that are. Yeah, probably maybe the 4 as well. Take a look at the actual Okay, now, one of the things it asks you to do is before we do any of these, looking at the structures, use your chemical intuition. Which one do you think is gonna be the lowest? Make a guess before you do this, before you actually run all the calculations.